Then Eric Boyd of Internet 2 is going to talk about primarily about the future offerings from Internet 2, specifically AL2S and a couple of other things. Then Nick Bastin is going to be talking about a framework for developing SDN within the context of software switches. And then I'm hoping that we can have an open discussion here in this group. Maybe you want to move down a little bit in order to facilitate, because we don't have a microphone, to sort of go from where we're at right now to providing to experimenters the kind of SDN platform that we'd like to be providing. I'd like to do that soon, and I'd like to do that aggressively. It's something that you've heard a lot about the solicitation for tool awards that have happened. Solicitation for will be starting very, very shortly in a number of different offerings, and a number of those are tied into providing capabilities and adding to existing capabilities, to existing tools, the ability to tie in SDN more readily, to make it easier to build topologies that are where the flows are software definable. So just to get all on the same page, what are we talking about? What are we really trying to provide here? I want to describe these as sort of an ends. This is what I think we want to be providing. We want to be providing experimenters with user-specified programmable WANs, wide area network capability. So they are providing the topology. They want to say, here's what the topology that I want, and here's the nature of the programmability. So it's a collection of network resources, links and subnets, and however you want to put them together in sort of the standard way. But we want to be able to provide them with the ability to program the forwarding decisions of traffic that are going to flow across that WAN. Typically, when we talk about SDN, we're talking about open flow, but obviously that's not the only way that works. There are other ways for that to be happening. So keep your minds a little bit open about what we mean by programming the WAN. We want to make sure that the traffic on your WAN is logically segregated from my WAN, so that we can both be doing this, and we can both be making sure that our traffic and also the routing decisions and the way that I have programmed mine doesn't interfere with yours, even if we're co-located on the same physical resources. And finally, in order for this to be a meaningful capability, something that an experimenter really wants to be able to do, we need to be able to have the traffic that's on this WAN visible through standard network monitoring tools, so that I can actually see what's flowing from one part of my network to another part of the network. What are the pieces that it's flowing through, so I can have full visibility into what's happening, so that I can tell, is my algorithm working as expected? Is my controller working as expected? Is traffic working as expected, and so on? And finally, this is sort of a thing that we're always saying about any aspect of GENI tools. We want to support experimenters in two dimensions. One, when they want to do sort of the normal standard things about SDN in tutorials for beginners or what have you, we want to make the simplest things simple. And right now, I think we would agree it's not that simple to set up an SDN topology. We want to make the common things easy, and we also want to make cutting-edge things possible. So those are the things I'd like you to keep in mind as we talk about what we're going to be trying to get from where we're at right now. And after Eric's talk, and after Nick's talk, we can sort of open up where we're at and how we can get to where we want to get to. So at this point, I'd like to talk about, to introduce the two speakers. I've got these flipped on the slide. I apologize for that. But Eric Boyd from Internet 2, he'll be talking about current plans and expected features for the Internet 2 offering in support of what we're going to be providing to experimenters with GENI SDN. And then Nick will be talking after that. So, Eric, let me switch over to your slides.
Just give me a second here. There we go. All right, now we can start. My name is Eric Boyd. I'm the Senior Director for Strategic Projects at Internet 2. I'm going to give a little bit of an overview about what Internet 2 and GENI have been doing and what we hope to be doing together going forward. Luke Fowler sitting over here and Matt Z sitting over there help me put some of the slides together here and are here as well, and can answer questions too if you don't catch me. But feel free to interrupt as I go. Try to walk through a little bit of what we've been doing, but I welcome your questions during or at the end. So generally, what are we trying to do at Internet 2? We're trying to create an environment in which all sorts of applications can take advantage of a nationwide 100 gig network and encourage a climate of innovation. That includes, in particular of interest here, creating and supporting an environment for network research and driving new forms of networking as we go forward. So specifically, Internet 2 has traditionally offered a layer 3 service. It's a for those of you who aren't familiar with it, I know that's not everybody in the audience. Basically, we provide a national network. If you're connecting between two universities, you're probably going over our network. Your university may not have a direct connection into Internet 2. There's usually a regional network in between. And so you'd go through that or an exchange point on the way through the Internet 2 network to another campus. So the blue dots are a traditional layer 3 service. The red dots are our layer 2 service, which we rolled out just over a year ago, I think. I think there's 22 dots on there, although that number continues to go up. And on that, we're offering basically a production layer 2 VLAN service. The interesting thing about it, it was the first nationwide 100 gig SDN enabled layer 2 service. So all those nodes are fully SDN enabled. So that's how we're offering our layer 2 service. And actually we're in the middle of migrating the connections as shown in this map between our layer 3 nodes to actually run over that layer 2 service as well. So that's a long way of saying it's a production service and we really care about it because it'll also break Facebook. But what do you care about from a GENI perspective? Traditionally, we've offered a layer 2 service called ION, which was implemented over MPLS on our routers. At the last GEC, we announced that we had deployed the Max aggregate manager on that so that you could start provisioning VLANs via the GENI API over ION. But folks are increasingly buying ports directly onto the AL2S network. And so what we demonstrated last night and are happy to announce is that we're now running, thanks to Luke's efforts, we're now running Foam as an aggregate manager over AL2S as well. And I'll have more details on that during the operations session this afternoon. But basically, we're supporting 2 aggregate managers and working towards fully supporting stitching by the next GEC. And so the demo we showed last night, just to show you in brief, we went from an InstaGenie rack at the BBN offices through the New York router across ION, where we use the aggregate manager from Max to provision that VLAN, and then back from LA to Atlanta using the Foam aggregate manager over AL2S. So that's now working. So now a little bit more about SDN and innovation. Basically what we announced about a year ago is that we wanted to create a 100 gig test bed for innovation. And so one question a year later is sort of how well are we doing? The 3 pillars that we identified as the components of innovation are abundant bandwidth, the ability to encourage application innovation through programmability, e.g. SDN, and support for data-intensive science. And by that measure, I think we're doing okay. There's been a lot of synergy with the NSF CCNIE program. There's been a lot of grants going out there to them. And likewise, we've been working with Indiana University, ESNet, and others to put together operating innovative networks workshops, which John Paul's had a big hand in. So I think we're making a lot of progress in this space. But really, what I'd like to talk about is, where are we going? Do we have support for network virtualization? And that's going to be the bulk of my talk here. And down the line, can we start integrating the network with compute and storage, which sort of I won't talk too much about, but you could think of as a future thing we're trying to get to. So a little bit about network virtualization. This is our fancy graphic to sort of show we're trying to create a sliceable network. So specifically, what are we trying to do here? We've had virtualization of storage and servers for quite some time. And what we want is to support network virtualization as well. And this is a quote I dug up, basically sort of giving the basic definition of virtualization from about a decade ago. And I think it still holds up reasonably well. So what does that mean in a practical sense in the SDN space? We want to decouple the control plane from the data plane, and we want to enable multiple virtual control planes on a common physical data plane. So let me back up and say, what does this mean in terms of money? We don't want to build separate private networks going forward if we don't have to for network research, for high energy physics, and for Facebook, right? We want to have a common network platform that can meet the varied needs of our community all the way from at one end of the spectrum, just simple commodity communications between students, to the other end of the spectrum, be it data-intensive science or support for network research. So we're going to dive in a little bit towards that. And as a bit of a preview, we've been in partnership with Indiana University trying to build and deploy an architecture to sort of support the idea of sort of multiple VLAN spaces as we start slicing up the network. So basically what I want to sort of start with is to walk through what we showed last night, which is not yet deployed on that full AL2S backbone, but is really close, and then sort of show sort of how we got there, the software stack we used, and what it means for researchers and developers going forward. So traditionally, and I'll show some better slides about this a little bit later, we've shown our OESS controller, which is how we implement that production layer 2 service over a heterogeneous mix of brocades and junipers in SDN mode. Was there a question? Oh, okay. So we've shown the OESS controller over that mix of heterogeneous mix of brocades and junipers, and so that's how we've been implementing that 22-node nationwide SDN-enabled layer 2 service. But what we want to do is we want to be able to take other applications. Here, what we used in the demo last night was Martin Swaney's XSP application, and run that as well if they want to do their own controlling. So in some sense, the first bit of what I talked about in the first few slides was, if what you want is a VLAN between two racks, we can, the Internet 2 backbone is now participating in that, and you can use an aggregate manager to ask for that. But if what you want to do is a little bit more, if what you want to do is actually deploy your own controller on a 100 gig nationwide infrastructure, albeit with a limited slice of resources, we want to give you that environment as well. And so what we showed last night is that we've developed a tool here called Flow Space Firewall, which you can think of as building off of some of the early work that's been done with FlowVisor. It's sort of targeted at a slightly different use, and I'll talk about that more in this afternoon's talk, a little bit about why we did that. But it's basically a VLAN slicer that allows you to sort of run non-overlapping sets of VLAN ranges. So here we were showing on a 3-node system, two brocades and a juniper that's sort of akin to AL2S, but in the Bloomington lab, which were paid for by the iDream grant from the GPO, running sort of a local instance of OESS as if it was a 3-node network. And at the same time, we showed last night, so this would be the XSP application that Martin and Ezra put together, and you can see again that same triangle, and they were running their application as well. And so the idea here, going back to here, is that if XSP asked for a VLAN or tried to insert flow rules about a VLAN that it was not allowed to, i.e. they were part of the production infrastructure, that would get rejected, and vice versa. So we don't have this quite deployed on AL2S yet, but that's sort of, I'll talk a little bit further where we're going with that. So a little bit about our software stack next to say how we're sort of getting to this point. So our network is a set of OpenFlow switches, and we've been using OESS as a controller. And you can provision a VLAN across OESS using the OESS UI. And while the GENI researchers may not do that, that might be of interest, for instance, to two regionals trying to set up a permanent VLAN between themselves for some sort of peering. Or it might be useful on demand for a high-energy physicist seeking to do a big data-intensive science data transfer. But you could imagine an experimental app that was just directly talking to the OESS API, and that's a perfectly good thing that a researcher could be doing. We also have sort of integrated with OESS the Oscars protocol to give us the IDC protocol that allows us to provision across ION and partner links. And so you could have an experimental app coming in through the Oscars API as well. They made a bit of a typo here. I said that they could today also come into the NSI interface. While that's been deployed in an experimental way on manland, we haven't yet deployed it on AL2S, but that will be coming shortly. So these are some of the things you could have done as of this summer in terms of the ability to use the network, all of which are just different ways of saying I'd like a VLAN across the backbone or integrated along an end-to-end path. So what I talked about in the beginning of the talk here, this is sort of saying it in a different way, is we've also added the phone controller over here. And so what you can do is use Omni or something like that to essentially get a VLAN via the aggregate manager. And yes, there's SDN under the hood, but you're not really interacting with it. So where are we going next? So what I've added here is flow space firewall, and in some sense, I think of that as sort of a one-to-many mux. I don't know if that's really the right terminology, but basically, it's a way initially that just act as a pass-through for OESS. But what we hope is to be able to grab a slice of it using foam as we move forward. And so therefore, what we're hoping is by the first quarter of next year, that you see now there's a new type of experimental app which would basically look like an open flow controller. And if we had grabbed the slice with it, then you could be able to continue to your experiments on the national backbone. It's not full control, but it's a lot closer to full control. And then this is just to say that there's nothing, if you really want the functionality of FlowVisor, you could do that as well. Just run that inside of a flow space firewall slice, and then you could sub-slice if you wanted as well. So whether we run a production instance of FlowVisor or we just let researchers deploy it if they want to, I'm not really sure yet. These are some of the things we're just starting to figure out. So what would that look like in terms of a software stack timeline? I put the word draft here at the front just as my big hedge to basically say we're trying to work all this out. This is my best guess at this point. We will continue to evolve this both in discussion with our community and in discussion with the GPO. But this at least seemed reasonable, is that from a rollout perspective that we could be deploying flow space firewall on AL2S by the end of the year, running the first experimental applications by early next year, and doing it over flow space firewall towards the end of that quarter. From a service perspective, which is actually, I think, more interesting, what I expect to see is that after we deploy it, we will be burning it in by deploying our own applications, which might be working with a partner like Martin or somebody else here to try it out. And then we'll be working with the GPO, as I'll talk about this afternoon. Louisa did a lot of work testing the deployment of foam that we had over OESS. And so the idea would be to go through sort of an internal test phase, then work with the GPO, and then start rolling it out with experimental apps at that point. What I do expect that we will do, though, is you notice I use the word testbed validated there. Even though we've tried to build flow space firewall to give us good protection, what we will do, at least in the early days, to get confidence and to breed confidence in our community, is if somebody wants to take advantage of this, is first work to deploy their code, probably on our NEC testbed called NDDI, and then maybe after that deploy it on the iDream nodes in the lab and just make sure that we've really got a rock-solid environment as we take baby steps towards sort of making this a reality. And then, for those, I tried to come up with sort of what that process might look like, at least in the early days. So really the goal here is to run experimental controllers on an at-scale nationwide production network so that we're using a common infrastructure. And the way we think we can get there, first we need to have a community conversation. It's not just with the GENI community, it's also with our production community in a sense. And make sure that we're talking through what we're doing. This would be part of that conversation, but we would have more focused and detailed conversations going forward. Just so everybody has the same set of expectations and understands the test regime and the gentle rollout as we bring it into operation. But what you might start seeing in the first quarter of next year would be you would basically contact the NOC and say, I want to do this. I want to deploy my experimental controller. We'd first deploy it on a test bed, probably NDDI, and then moving to the AL2S-like iDream infrastructure, and then work with the experimenter to develop a test plan, validate that we think it's good to go in the production environment as we get our comfort level up, and then start running the experiment on AL2S. So obviously this is a slower cycle in the initial days than most experimenters would like in terms of trying to hit paper deadlines or change code. So we're very sensitive to that, and we'll try to work with you on that. But we also have to sort of have a gradual way of working up to this as we go forward. So I promised, hopefully kept it short enough. So basically what we're trying to do is be able to say that, yes, we're supporting network virtualization going forward. And then we can start trying to figure out how we bring in the compute and storage resources as well into the network. So let me stop there and see if there are questions.
When you say you have a layer 2 end-to-end sort of network and that a VLAN can be persistent across that entire topology, in my head I say, wow, that's a lot of stuff because there's a lot of nuts and bolts there. And so are your primary mechanisms remapping VLANs? I mean, are you doing Q and Q tagging? I mean, what are some of the mechanisms that you use to make that?
No, we do not currently support Q and Q. We need to have OpenFlow 1.3 support to be able to do that. We don't support QoS either. I don't know, Luke, do you want to?
And yeah, as far as mapping, there is a pervasive VLAN translation. So if you get something across the L2S backbone, you can use any VLAN tag on any endpoint, and it'll transparently translate across the trunk side to avoid conflicts.
So can I ask a quick follow-up? Does that mean that are you leasing lines from providers?
No, we own our own fiber.
Yeah, is that right?
Yeah,
It's a little easier.
so for those folks who aren't aware, so with the 2009 stimulus program, they had the BTOP program, which put about, I think, $1.5 billion into the R&E community in general, much of which was used to purchase fiber. Internet 2 in particular had a $100 million upgrade, and is now owns, I think it's 15,000 miles of dark fiber, and it's leased an additional 3, something like that. So yes, we do have a nationwide network. The additional piece that's new is that through Montana piece. But yes, as opposed to where we were, say, 10 years ago, we're now on our own fiber. And so what we're offering on that fiber is a nationwide layer 2 VLAN service, a nationwide layer 3 service, and we're also offering our transit rail CPS commercial peering service. Oh. Okay. I am happy to take any questions afterwards. Just grab me at the break.
I just found out we lose this room at 12:15, so I apologize.
That's okay. Thank you very much.
Audience for this talk, which is I'm trying my best to hit at least 3 different audiences, so at least a third of you, maybe 2/3 will certainly be bored at any particular time. Don't worry about it. We'll talk about some of the goals of what we're trying to accomplish, although Marshall has already talked about a lot of them, but I was outside, so I missed that. So I'm probably going to go over them again. Then we'll talk a little bit about the architecture and how it works at a high level, and then how all of you can help. And when this thing runs out of battery, we'll be screwed. Seems to be low. So the goals very basically are more flexible topologies. Right now you have, one GENI WAN, it is the WAN that it is, and you have to make your topology work within the confines of that, or you can live inside a single rack and, do as much as you can there sort of virtually. Enhanced data path programmability. Right now, obviously, you're stuck with whatever you get from FlowVisor if you want SDN stuff. And if you don't want SDN things, you get VLAN slicing and stitching, but that's pretty new. Some increased visibility into your network. This is a serious problem now if you're an experimenter. We'll talk a little bit about that. And then the ability to use some standard tools and management, and then enable sort of research we can't do right now, which sort of pushes us closer to the cutting edge of what networking is doing now. So the GENI WAN is your oyster, or something in this case. The whole point here is that we build a virtual topology that allows you to use the racks in this case, although we may expand the resources available as, thank you, perfect, that allow you to use the racks as vertices in an arbitrarily edged graph, basically. So you get a full mesh of rack edges and you can construct your topology out of that. We try to do some magic behind the scenes to avoid massive oversubscription, but we have actual physical constraints in the network. And then potentially in the future there will be some decision points in the core network. Newer hardware is being deployed at NLR specifically that might allow us to do some more creative things. So one of the objects here is to allow users to create topologies and then use any data path implementation you like, including non-SDN. This is in fact why the talk is sort of called virtual network topologies, is we don't care what you're going to do with them, we're just building a topology. You plug virtual bridges into them, and those can be anything you like. If you want it to be OpenFlow bridges, you can choose a pile of existing software OpenFlow implementations, some of which are highly performant. If we can work out the licensing problems, or individual experimenters can work out licensing problems, Cisco 1PK is certainly an option. We've done this in tests. You can stand up normal click router experiments this way, and you can integrate sort of standard middle boxes as first-class members of your GENI topology. So there are VM versions of many middle boxes that exist in the world, so you could get, a big IP load balancer, checkpoint firewalls, all sorts of devices, and sort of throw them into your network and do research based on, working around those types of devices. You could do WAN accelerators, that sort of thing, packet engines type stuff. So programmability, we'd like to allow you to use a completely custom data path implementation. If you want to do research into writing actual switches, then you should be able to instantiate a node in the network that allows you to forward any way that you like using any protocol that you like. That's a piece of research that we should allow you to do, and you should be able to embed that in your WAN topology. And then, of course, a more common aspect would be the ability to create and deploy extensions to things like OpenFlow. This is what people do a lot in existing networks, and so we should be able to do that as well. I mean, commercial implementations of OpenFlow very rarely are just OpenFlow. They're OpenFlow plus whatever sort of turnkey extension someone decided to create for their own applications. And so to be able to do sort of compelling research, we need to be able to get into that space as well. A little bit going with the ability to create custom switches and data planes is that you should be able to have arbitrary data plane pipelines. If you want to do ASIC research, you can do it that way. And then the ability, because this actually doesn't use FlowVisor, doesn't have a proxy, to have modern SDN control plane support. So you can do research and build distributed controllers, HA controllers, have failover, test failover, run failover scenarios. Things you can't really do now because you can't force FlowVisor, except in really mean ways, to disconnect from the switches it's currently connected to. Or if you did, that would not be nice. So increased visibility is another goal. This is a very serious problem with what we do now. Even if you're happy with like the OpenFlow implementation you get in GENI today, you have no idea what's going on in most of your network and no good way to find it. Sometimes you can send an email, make a phone call, get in touch with an operator, and get access to debugging information if something has gone wrong, but sometimes you can't. If you have packets and you want to know what your LLDP looks like between NLR Atlanta and I2 Atlanta, no one can help you out. There's no tap there. There's no way to capture packets there. So one of the things about this is we end up using L2 pseudo wires, so all links in your topology can be tapped and monitored in isolation from other slices, so we don't have to worry about giving you data from other people's slices. So you can TCP dump them on demand or do anything you like. Because we're giving you virtualized containers with your bridges in them, you can have full code level access to debugging your bridge if you're writing your own bridge, if you're building your own ASIC, that sort of thing. And again, no control plane proxy. So no FlowVisor getting in the way. Like right now, if you have a problem with your OpenFlow controller, you can obviously get a TCP dump of your control plane from your OpenFlow controller to FlowVisor. But if it doesn't work right, if you get EPERM back from FlowVisor, you have no idea whether FlowVisor sent that to the switch, and the switch sent EPRM back and it just propagated that back to you, or whether FlowVisor told you that and there's some log entry that you can't ever access that tells you why, or maybe it doesn't tell you why it did that. A lot of visibility you lose here, which makes using OpenFlow right now a real pain in the network. And then we want to increase the visibility of the underlying infrastructure here. So obviously what we're doing is creating you a virtual network topology over some underlying infrastructure that you're sharing, and it needs to be clear to you what was going on when that was happening. So if you want to look at your experiment and say, I got really odd results there, but at least I can go back, see what path my virtual network took, and then look on that path and see if there was, lots of congestion or something that can explain my results. So we want to offer the ability to have standard tools support. So right now, because obviously FlowVisor sits between you and the switch, even if your switch supported SNMP, you wouldn't be able to manage it that way. You don't own the switch, the administrator does. You can't get SFlow and NetFlow data, that sort of thing. With these virtual network topologies, the whole point is you are the sole owner of this virtualized bridge. So you can use any tool that you like. You can deploy any change management system that you like, any monitoring system that you like. You can integrate it with, whatever you're using to manage your hosts, anything like that. So you can find out if you have, monitoring problems across your entire infrastructure, hosts, and VMs and bridges. And then the bits about enabling sort of research we can't do right now, or a real pain to do right now, you basically have to build this up yourself, is certainly IPv6 is a big one. You can work with MPLS. I'll talk about this in a little bit, but you can work with any layer 2 that you want. It doesn't have to be Ethernet. You can get end-to-end QoS for real at moderate data rates anyhow. I mean, if you want end-to-end QoS at 10 gig, you're going to have a little trouble because we don't really have 10 gig end-to-end to start with. You can mess with flow control. You can access a wide variety of versions of OpenFlow because you can stand up these software bridges. I want 1.0, I want 1.1, 1.2, 1.3. Future, you can have all of those things. You can, like 1PK and other implementations, you can have non-OpenFlow SDN implementations. As they become more popular, we probably should make sure that we can implement protocols across those things. And then you can have non-SDN platforms. You could run the Linux bridge if you wanted. You could run, a click router. You could run any number of things. You could operate your entire experiment at L4 if you wanted to. A lot of flexibility there. So how it works is very, very, very basic. It's a combination of L2 pseudo wires and virtual machines, which is to say that you can do this exactly now yourself, except that you spend a lot of your time building up this infrastructure yourself and not doing your actual research, not doing your actual experiment. You should spend your time doing research, not building infrastructure. That's what we're here for. So basically what happens is we stand up virtual machines at all of the places where you want to bridge, or we share a different, there's actually a number of different ways that this gets done, but just imagine that it happens this way, sort of for a high-level abstraction, is we stand up virtual machines at every place that you want to bridge, we instantiate the bridge image that you care about, and then we plumb your pseudo wires into it. There's, again, as I said before, some new core hardware coming online that has better slice isolation support. It will have limitations on what we can support, like, if it's not a Cisco box, it's not going to support a Cisco image, but we can still be a little bit more creative than we are now. So there'll be an aggregate manager that exists at every edge like there already is, and tools to set up bridges and paths for you. And then we'll use every available existing GENI network resource to set up paths. So when we set up a sort of example, it was using the existing OpenFlow core. Now network stitching is available. We can get, stitching is actually less important to us than the existence of dynamic circuit aggregates. We don't want the stitching tool to do our work for us, but the fact that we can provision circuits with ION, Oscars, and AL2S gives us a bunch more paths to sort of try to keep experiments from contending with each other. And then we can also provide reasonable backup paths. So if you ask for, a connection from Stanford to Wisconsin to BBN, and there's a bridge there, and then we lose the primary path, because we have a pseudo wire, we can just make sure that your packets still get there even if we choose another path. And we'll try to be really clear about this in the manifests about what happened to your experiment over time if your path changed. I'll get that. So this very simple slide explains the network architecture. Very easy to understand. You have a full mesh of, you have a logical full mesh of network, and you can build your graph out of this. So if you want to build this topology, your experimenter can define your graph using any vertex that's available, in this full mesh topology. Obviously, it's not really a full mesh, but we're building that logically, so those paths are available to you. So just quickly to go over the pseudo-wire implementation before everyone freaks out. I've broken it up. The blue at the bottom is what the existing infrastructure in sort of an abstraction already does for you. There are places where, for example, we're already getting L2 over MPLS. Then what we'll do is add another label on top of that, probably MPLS, but it depends on where we are. There are other more efficient options in some places. And then your experiment stack exists on top of that label. The key point, as I sort of mentioned before, is everything above that is completely defined by you. So if you don't want your L2 to be Ethernet, it doesn't have to be Ethernet. If you don't want your L3 to be IP, it doesn't have to be IP. We don't care. You want to run fiber channel, you want to run ATM, have at it. There are some realistic limitations on how you can implement this in certain data paths and certain VMs, but if you're persistent, you can make it happen. And then the second bullet here is kind of important. It's opaque to the core switching devices. We continue to run the infrastructure as actual infrastructure. It doesn't have to know about whatever crazy SDN or non-SDN type thing you're trying to do in your network. And if you want the full range of all VLANs and the full range of all ether types, and you can have them all. The only place where it matters is where you interface with the public internet or the control plane. So we do the heavy lifting of unrolling all your pseudo wires at your interfaces, basically the ports on your data paths and the interfaces on your virtual machines. The one key obvious point is if you use bare metal nodes, things get a little hinky. You need to, obviously you can't run ATM to your bare metal node, so you have to transpose, first of all, to a layer 2 that your bare metal node supports, so that's probably going to be Ethernet in a rack. And you probably have to deliver it over a VLAN that you've provisioned another way in the rack as well, or your bare metal node has to participate in the pseudo wire. I think typically that middle case is what will happen. If you really, really, really want bare metal, then you'll just truck that over a last hop VLAN inside your rack. And that's a situation we can support pretty easily. So the GENI pieces, to bring this back into how you interface with GENI now and how you build experiments now, is that there's always an aggregate manager. We'll just make more. Use all you want, we'll make more. We make another aggregate manager at each site that has a resource effectively available for pseudo-wire gluing, as it were. That's usually just a rack. Your request RSpecs will specify simplex pseudo-wires. All network edge connections are simplex, so if you want connections in both directions, you just make them in both directions. And then you specify what data path image you want to have stood up for you. So then a VM is stood up, your data path image is put on, your pseudo wires are glued into it, and everything magically goes away. You don't have to worry about it. And your labels are only locally unique if you're pondering this problem, so you don't have any impossible tool coordination, global coordination problems. There are a few limitations. In reality, you must have a data path at each site where you have compute resources. It's really only a should, but you'll have to do a bunch of heavy lifting yourself to use some existing GENI network technology to get that compute resource connected into your WAN. You can't specify L1 paths that you want the pseudo wires to use right now. In theory, this is possible. It's, for the most part, overly complex for the experimenter. And then doesn't do a good job of allowing us to sort of balance resource utilization. So we can look around and say, well, we've already provisioned paths of a gigabit over here, so we'll try to use a different path. But in theory, we could offer this functionality. And a small problem, a tiny itty-bitty problem, is you can't actually reserve any of this right now. It doesn't actually exist for public experimentation. I don't know if Marshall said anything. Hopefully by next GEC, we'll have a demo, at least. Maybe something available. We'll see what the timeframes look like. If there are tool writers in this room, a plea to all of you, and all of you who might ever be a tool writer or want to aspire to be a tool writer. Topology creation and resource coordination are a pain. They're a pain now. They're going to continue to be a pain. If you want to build this network, you're going to involve a lot of aggregate managers. You're going to involve a lot of RSpecs, and you're going to talk to a lot of things. We'll probably create a sort of very basic set of tools, but they're going to look a lot more like Omni and a lot less like FLAC. So if people start wanting to build topologies, in sort of graphical ways that are sane, we could use some help. The documentation and RSpec schemas for how you interface with this will be available after GEC, this GEC. And hopefully a beta deployment will be available before GEC19, but I don't know when. We have to decide on a bunch of things with GPO and with resources and stuff like that. Oh, that's it. Excellent. Any questions? Sweet. Oh. Bill? That's what I was worried about. You get one.
Yeah, the one that takes to mind is, how do you see, or do you see it being possible to extend this infrastructure outside of the traditional GENI infrastructure into a cooperative campus?
Sure. The campus, this is like sort of what we talked about in the past with racks and having campus resources and that sort of thing. You have to have some way to peer. This is your classic problem, right? So if a student knows how to get a campus resource and knows how to label it properly to get it into the GENI space, either putting it on the right VLAN or whatever, then once you reach that GENI edge, then you can glue yourself to that GENI edge. Obviously, we don't know anything about the topology beyond the GENI edge, so all I can do is get you here and throw packets onto the floor, and if they pile up in your data center, that's your problem. So, Heidi?
So just to clarify that part for what we're doing with campuses, right? This is a little speculative still.
Yeah.
So we are not going to campuses now and trying to get them to implement this or extend it or anything like that. This is, make it available and see if people like it and then deal with that. So don't camp it.
Yeah.
I see more promise than threat.
No, I think so.
Yeah, it's just you want to do this in a phased way.
Yeah, there's a huge amount of unknowns there. But my answer will sort of always be the same, which is we'll get you to the edge, and whatever we figure out about how you access campus resources as a community is presumably how you get from that edge onto the next thing.
Any data on the interoperability of the 1PK infrastructure versus other SDN topologies or other these topologies?
So far as I know, there are no publicly available controllers which can talk to both. They do exist. And that's actually would be one of the upsides for trying to make that happen, trying to work that deal out, basically, would be more availability of controllers that could speak across SDN platforms. We already have this problem, right? If you have an OpenFlow 1.3 switch and you have an OpenFlow 1.0 switch, it might as well be, a 1PK device. It's just about that foreign, between the two of them. So while there's nothing available off the shelf now, I see this as sort of fertile ground for opportunity for sort of building coherent northbound interfaces on disparate southbound protocols, control plane protocols. Nikki?
So you talked about that this is going to be a different AM.
Yeah.
And how do you imagine this to work? Will it take the RSpec from the user and then you talk to the other AMs? Or you get
Oh, no.
portion of the AMs that are only for you and you manage them?
Right, like getting OpenFlow resources now, right? So like I want a piece of flow space at this foam, I want a piece of flow space at this foam, I want a piece of flow space at that foam. There's no global coordination involved. That would get done by a tool. My hope is that we will provide at least the basic tool that allows you to write one RSpec and then talks to all the right AMs to do it. But you're going to talk to a bunch of AMs, kind of like stitching, right? So like you ask for this path in stitching, and then it goes around and figures out how many AMs it actually has to talk to in the middle to figure that out. Creates this sort of build execution order for Omni, and then Omni executes all that.
So you build a
That is certainly my intention, is that I really want people to be writing one RSpec.
And then the user actually talks to the individual AM.
Right, yeah. Yeah, there's no global coordinator. There are all sorts of sort of GENI architecture-related trust issues if you try to do that sort of thing.
We can take it offline if it takes too much, so it's too detailed, but we talk about an AM per run.
Yeah. 1 AM per administrative site, right? I mean, that's really what we're talking about.
And this is separate, that's what I try to understand, we'll have like local resources dedicated only to this AM.
Yes. I mean, pseudo-wires, much like flow space, are kind of ephemeral resources, right? I mean, like, yeah, they're pseudo-resources, exactly. I mean, so what it is a provisioning machine, right? Like, you give it an RSpec and it knows how, at that local resource, to make this happen. Either because there's some special facility of the switch on the rack that we can use, or because we've reserved some VM that we do the plumbing on, or because we have some dedicated bare metal node we do the plumbing on, like whatever that is, you don't have to worry about that. We just make sure that the topology you asked for actually gets created or gets rejected.
Yeah, I'd like to follow up on the first question in terms of university accessibility.
So is it possible to have like small prototype at university where a student can get used to it so that when we need like to connect, people are ready to
It would be possible for you to build one. All the software is open source. Whether we will build a sort of virtualized environment, that seems like a very serious stretch goal. You could, in theory, stand up this sort of thing in like a mini net. It would be complicated. But it could be stood up on a small scale in some local lab. But yeah, I mean, that would be sort of a thing that probably individual sites should talk about. I don't imagine that we'll ship some sort of magical installer that makes this happen for you. But I'm sure we can give guidance on how you might want to do that. Marshall?
So we've got an issue now with some of the existing aggregate managers of image management that on InstaGenie there's a set of known images, and on ExaGenie you give it a URL. I think we have a similar problem we should at least talk through, that this infrastructure presumes that you are coming to the table with the images for the bridges.
Well,
And
not exactly.
So we may or may not have to manage a list of canned bridge images,
Yeah.
or you providing URL. So there's no fixed set of bridge images, as I understand it.
I imagine we will come to the table with a set of bridge images already ready to go, because some of them will know how to optimize in particular ways. But it won't be a fixed set of bridge images in the sense that you can't do anything other than these. So in that way, yes, we have an image distribution problem where we have to think about, I mean, I'm perfectly happy of using the system of you give us a URL and we load your image from there, but then there becomes this question of where is that URL and how are you as an experimenter, finding a place to put these sorts of things. Lee, you guys, what do you do for the image serve? You make it on one rack and then you serve it up?
You make it on one rack, you can convert it by URL, and then it gets dragged across.
Yeah, so we could potentially do the same thing, actually, because one of the options for this is to stand up an empty container that all of the pseudo-wires are glued to, but which has no bridge in it. And it's just a Linux box of some sort, right? And then you can log into that thing, stand up whatever bridge you want in it, including your own custom code, and then potentially tell us that's an image, and then we can make that available to other places. But you'll have to have this multi-stage process where you build one, and then we can deploy it other places. But it's certainly something we need to think about. Anyone else? Tim?
I'm curious about the dynamic provisioning at the physical layer of the network, especially the experimenter view. You had mentioned that you would prefer to use something like direct access into like an IDC instead of,
Well, I'm happy to use the Max AM or the OESS AM. I just think we're unlikely to use the actual stitching compute service, right? We're going to make our own paths.
Well, the question I have is, who's responsible for provisioning those things? Is it an operator ahead of time, the AM that gets the request, or a tool?
Well, it's a tool, right? So like this larger RSpec that you've asked for, this topology, we process that like with stitching. We process that through effectively a topology computation service that determines where we're really going to put things. And then you're handed back a set of operations for a tool to execute. I mean, and there's no, just like with stitching, there's no requirement that a tool use that topology service. It's easier for Omni because obviously Omni doesn't have a topology service built in. But if some tool like FLAC or Flukes or something had their own idea of what topology looked like and their own way to compute what paths they should make, you know, so be it. All we're really doing is provisioning. I only care that a path is actually there and can actually carry my label. You know, who provisions it sort of doesn't matter, and what it's transported over sort of don't matter, so long as I can glue it to a VM on each side. Marshall?
You said what about the labels? You mentioned that you thought that the labels would be opaque and that we don't have a global problem with label space, but at some point we all have to agree on the same label within my slice.
We don't. So every pseudo wire gets its own label. It's not like your slice gets a label, right? So every single simplex pseudo wire gets a label, and the reason they only have to be locally unique is because it's the culmination of a label and a destination MAC address. So labels are, right, exactly, they're point to point. We're not pretending to provision some sort of multi-point magic hub wire. I mean, if you want, you know, multi-point LAN type access, that's what you just make your bridge do. I mean, these are the actual wires, right? So then each AM keeps track of the labels that it's handed out, and it doesn't matter if they conflict with other AMs because they won't be on the same path. Bill?
Is the path computation part of this why it's so important that we have accurate attachment info?
That's, yes.
I'm beginning to put things together now.
Yeah, things are coming together slowly. We may try to run, I've already started running a slice that tries to tell if the attachment info is wrong by seeding it, you know, with LLDP information and then seeing if it matches what I find in the actual RSpec. But that's not a panacea. There's still some places that like LLDP doesn't work right and some stuff like that. So the attachment info is really important. The attachment info will also become really important when we can identify where existing OpenFlow points, for example, meet ION endpoints or AL2S endpoints that then we can use to stitch effectively to. There are these places in Internet 2 where we can, if we know the endpoint URN, we can effectively stitch to the port from AL2S that an existing I2 OpenFlow switch is sitting on, and then get right onto the network that way. But then we have to know that's this is also a multi-stage provisioning problem because you have to know that you must provision some paths first so that you can be told what VLAN they use so you can, you know, provision another path. And that's also why, while all of this is very possible for an experimenter to do today, it's horrible. I mean, like, you would be spending weeks or months of your time doing this instead of doing, you know, actual research. We want to stand up this infrastructure for you so that you can do real research later, or earlier, as the case may be. Chaos? Yeah. I mean, the same way we do it now, which is to say that the same way you stitch between, you know, Proto-GENI and Foam in the OpenFlow is that you pick, you know, you allocate your compute resources, you get your own VLAN, we allocate new compute resources actually on the same VLAN, then they can talk to each other over L2, then we wire the pseudo wires together over whatever the exit point is for that rack. And it will be different at different places. I mean, I know best how we would do this with Proto-GENI. I know least how we would do it, you know, with Orca. I'm sure it's possible. No. No, I mean, we need to be able to get out to whatever we've decided the egress point for a rack is, right? Whether that's you can only stitch to this rack, then, you know, we have to provision a stitching path. a problem you already have. I mean, ProtoGenie has to be able to glue its compute resources to a stitching path already. I think the thing that's sort of missing here is that through the process of mucking with your RSpec, we've Trojaned your slice at ProtoGenie. And so our bridge VM is in your slice at ProtoGenie. So it's already connected to all of your ProtoGenie hosts. So then it becomes the egress point for your ProtoGenie host to talk to the rest of the world. Like, so you draw a topology you think you're drawing, and then we change it, and put this VM that's actually going to be your bridge. So then ProtoGenie does the heavy lifting for us after we change up your RSpec. Thanks, Lee. Anyone else? Bueller? I don't know what time it is, actually.
It's about 12.
Ah, perfect.
So I want to get back to the last slide of this. I'd like to gauge, first of all,
No, you won't.
interest in if you're working with the data, if you use it. Two, if you're not going forward, this is I think this is an achievable goal, and we're going to try to have a demonstration of this by the next GEC, but we're not quite sure all the pieces that are going to be needed, and we'd like to know. If they'd like to do this, and we'd like to help.
Well, I think the first step is, do you think this is useful? Because if you don't, I don't want anyone to help. We should just not do it. But obviously, if you think it's useful, I mean, I think it's very useful, and I think it's useful probably to a lot of people who aren't in this room as well, who haven't quite experienced the pain of what they have to do already. But certainly, to any extent that you're willing to help, it would be great. Was there actually a hand on the wall in the back, or was someone stretching? Okay. Well, that's a tool. I mean, right.
But I guess I misunderstood something, so I just want
Well, so there will be more documentation available after GC as well, which talks about these sorts of things. It is similar to what you can already do with Orca building virtual topologies, except that it doesn't only use Orca. Right, so like you can get resources from, in theory, any GENI aggregate manager, and then glue them all together. But yes, it's very similar to what that does. ProtoGenie has a very similar service where you can get, a nationwide VLAN. Obviously, the other goal here that's different from what Flukes and Orca do out of the box, although as I said, you can do this as an experimenter already, is we intentionally make a distinction between a virtual machine that's going to be used as a bridge, a switch, a router, and a virtual machine that's your compute resource. Right now, obviously, you can go into Flukes and you can draw out a bunch of virtual machines in a path, and you can turn one of them into a switch. Right, so Victor's been, showed me some of that stuff as well. So that's similar, yes. Yep. Take all the help we can get. Uh-huh.
Are you assuming you are going to create a mesh layer to network among the racks first, and then you run your virtual?
No. We are basically just going to present it to the experimenter as if they can connect any edge to any other edge. We're not actually going to connect them if no one asks for it. Joe?
I do believe this is extremely important and valuable. So I'm answering that first piece of it.
Excellent. I mean, also, I would be happy to take waves from you.
And we would be happy to give them.
Well, if only we could glue those two needs and wants together somehow in the land of physical reality.
Well, let's work on that.
You and then Tim.
I think it is very interesting also, but what is the main difference between having somebody setting up a topology as linking multiple point to point versus using the tool to set up topology?
I mean, effort. they're fundamentally the same. That's what the tool's going to do for you, right? But gluing, if you think about it, you're effectively, if you do it yourself, you're thinking about the topology as it exists, imagining all the paths that you need to create, then labeling them and making them and standing that all up. And trust me, in our topology with the information that we have, I mean, even though we now basically have all the topology information, mining through it and deciding what you want to do in sort of a non-graphical way is really hard. And then you've spent a ton of your time building up a topology and not using it for what you want. You know, which is really what, if you're not like a postdoc, or you're not getting paid to do this, or you're not going to get, you know, your PhD if you don't do it, you're not going to do it. Like, it's too much trouble right now. Tim?
So, for the second question that Mark asked about, are people willing to help? I was curious if people could, or if you guys could elaborate on, you know, which pieces are built, which pieces are still needed.
Soon. I'm hoping to put together like a list of those sorts of things so people can look at them. I don't know if Rob is here, but we actually stood up an example of this in Emulab quite some time ago. So some of those pieces already exist. There's a lot of integration pieces that go with pieces of GENI that obviously don't look like Emulab, right? So there's a bunch of work to be done. But I think that most of the work that we would like to see other people try to contribute is going to be on the user-facing side to make it more usable. I mean, obviously by creating new AMs and new RSpecs, we're trying to make this process easier, but that's still making RSpecs and, you know, making people type XML and stuff like that. So that's pretty horrible. So I think most of what we want is going to be on the user-facing side, and hopefully tie into some of the solicitation for, you know, tools proposals that people have done, like I forget what they're called now, but there are people who are doing, you know, front-end user space tools for, you know, provisioning and that sort of thing, GENI experiment engine and stuff like that. You know, if we can leverage a lot of that work and just sort of enhance it to do this kind of stuff.
Just a little bit more, because what I'm imagining is after this GEC, or even after this session, we're going to gather together a smaller group of people who are trying to move this forward, and we will come up with a game plan, not with all the people in this room, but with some set of people that will identify tasks. Just as I say, we'd like to have a demonstration of this by the next GEC, and then we can evaluate it. How hard was it to build? How hard was it to use? How useful is it? But I think we need to get to that point to see whether this has the promise that we think it has.
Did you have another question, Nikki?
No, but I do have one in my right hand.
Damn it.
So are the pseudo wires are going to be implemented Topologies? So like
Where of it? Right. So if we use the existing OpenFlow core to route your pseudo wire, then we will implement it using OpenFlow. You won't know that, though. It's much like the AL2S ones are implemented using OpenFlow, but you're not aware of it and don't care about it. Effectively, what you're doing is getting tons of circuits. But I imagine that we will try to use like Max and AL2S a lot to get circuits, because we can get better paths that way, like more disparate paths to keep people from contending with each other. Although, of course, that's kind of mythical, too. I mean, like, a lot of those paths will be over the same physical links as well. So, Bill? Yeah. Right. Yeah. Yeah. Bill?
I have an observation. I'm just curious how you feel about this. On the one hand, I see a huge advantage to hiding some of the nasty details of how the real network works, like differences in OpenFlow implementations between switches, and lack of availability of VLANs across certain paths and that. On the other hand, I wonder if there's a risk of essentially creating a global mini-net, in that if this environment will be so perfect that basically anything will always work.
Well, I mean, this environment is going, have no fear. This environment's going to suck a lot. No. I mean, it's going to be over a real WAN still. There's,
So it won't be mini-net in the sense that, you know, there will be packet loss, there will be
right.
delays,
I understand what you're asking about, sort of like the magic of conformity, and of course I made everything work because everything was exactly the same on the control plane side, but I view that as an experiment design problem, not an infrastructure problem. You should have asked for something different. You know, you should not have asked for all of the same things, unless that's exactly what you wanted, right? But, if you want to do research into, OpenFlow 1.0 plus OpenFlow 1.3 plus, then you can do that with this. And if you don't want to do that, we'll wonder how applicable your research is to the real world. But you are left to your own. It's not MiniNet in the sense that you also, in MiniNet, you have no choice. You get one bridge all the time, and it's always the same bridge. We will give you choice, and if you choose not to avail yourself of it, there's nothing I can do about that.
So I actually have a flip side question. I think it was on repeatability.
Mm-hmm.
So I love this, it's make it much easier, and then I don't know exactly what I got. Maybe my experiment works this time and it didn't work another time because my pseudo-wire has got, I don't know, 600 more milliseconds.
Right, so I talked about this a little bit, I guess sort of obliquely, but your manifest will tell you exactly what you got. And in fact, one of the reasons to allow you to ask for specific paths is to potentially ask for you to exactly get that again. However, we have to be pragmatic and realistic about the fact that even if I give you the exact same path again, it doesn't mean the other experiments on that path are the exact same as they were when you were running it before. I mean, we have to understand how to analyze sort of the background noise when we're looking at our experiments. But we intend to tell you everything we possibly can about what that was, about what your real paths were, about what the load on those paths was when you were doing your experiment. Repeatable things on the WAN are hard, but we should tell you everything that you need to know to understand your own results each time, which we don't do a good job of right now.
With to end the session here, please use this door to leave and not that door. That door's locked, so please everyone go out this door. And I'd love to be at 12:30. Thanks, everyone.
Let's hope the fire people don't show up to talk about that.